Uh, all of that chat stuff is still there, right? That might come back though, I think.
Hey, Adam. Do you happen to know with the recording, can we get access to that later on? Or
We should, yeah. I'm trying to figure it out right now. Okay, that's looking live. How am I going to make this happen? Maybe this thing. Sure how to make this happen. Oh, there we go. Apparently, even though I don't know how to make it happen, I've made it. I always like it when that happens. There we go. And we're up. We're running. I love that we peaked at 18. Saudi Arabia was our furthest tune in. Huh? No, I don't think Matt was watching, but Todd Clardy was.
Oh, cool.
From King 5.
Very nice.
Yeah. He's a great guy.
Yeah. I checked some business stuff. I checked with Diego about the scans. Where he's going to put another one in like now, and then maybe another one later on. But we're just going to stop it at some point, and then tomorrow I'll have to just get the data in some form from you. can be Dropbox or
And then,
whatever.
are you gonna take the fish back with you?
Oh yes, yes.
Good.
I may
That'll save
ship
us
them
saving.
back. Oh yeah, no, you have to save them. I'm gonna
No,
pack
we
them up.
can stay with. Okay, we can ship them. I mean, we've got.
Yeah, I'm gonna pack them up for FedEx.
Okay,
And then
we've
they'll
got
be
a
ready
grant
to
that'll do
roll.
it.
I have a number as well, so doesn't matter. Actually, I should do it because we have a contract with FedEx. Our FedEx is incredibly cheap.
Oh, good.
Like a couple of bucks. So,
We'll take it.
yeah, right. Yeah, I'm gonna see Cassandra tomorrow. We haven't done any arrangements yet, and then today we said we'll dinner, but I'll check with her. Yeah, I haven't.
No, I
haven't met her.
told her.
Okay, no, I'll see her.
You'll see her in just a moment.
Yes, right.
You'll see her at her best.
My flight is about to 6.
Okay, cool. Oh, dang, that's great.
Do you keep a recording of this?
So it should be on the YouTube website.
Okay, Brooke was trying to watch me and she said that she can't find me on there anymore.
Apparently, it says it's 3 hours long and there's only 1.5 hours up there, but I suspect it's a processing issue and that it's all going to be up there.
Thank you.
Ready for the last.
Alright, hi everyone, I'm Amanda Herbert. I'll be talking to you today about the jaws and tooth plates of the spotted ratfish. Now this fish and its tooth plates were described over 100 years ago, but it turns out there's still a lot about it that we don't fully understand, including how they use these tooth plates to feed, and the overall shape and the tooth plates between individuals. So a little bit of a background. Class convictes are your cartilaginous fish, and it is made up of the elasmobranchs, which are your sharks, skates, and rays, and the holocephalids, which are chimeras. And my study species falls under the holocephali, and it specifically its name is Hydrolotus colii, the spotted ratfish. Now this ratfish is found in the waters right outside there, so you probably have to travel fairly deep to find it. But it is right out there, and it eats a wide range of prey, including polychaetes, crabs, sculpin, fish eggs, and bivalves. And what's really interesting about this is what they use to feed on these prey. And I'm not talking like forks and knives, I'm talking what they have in their mouth, what's going on in here, what they can use to eat such soft prey, hard prey, and complex prey. So one thing is holostylic jaw suspension. So this right here is an image from a CT scan of their jaw. And holostylic jaw suspension means their upper jaw is completely fused to their cranium. So to orient you to this photo, this is the lower jaw, here's the upper jaw, and here's the cranium and brachial arches. You can see no separation between the upper jaw and the cranium, and that's because of this holostylic jaw suspension. Now this is different from the jaw suspension systems we see in convictes, where the upper jaw can articulate with the cranium and can protrude. The second thing they have is tooth plates. Now we see tooth plates in some convictes, such as rays, where they have these flat horizontal surfaces that are great for crushing, shearing, great, good flat surface for that to happen on. These tooth plates, however, are these thin vertical plates that when they touch, they come into contact like this or like this. So not that flat surface we're used to seeing with tooth plates. So in this photo here, you are looking at the tooth plates removed from the jaw cartilage. You are still looking at the jaw straight on, so a great anterior view, same as the middle photo down here, but no cartilage in the leg. Now after looking at these tooth plates from many different Hydrolotus colii, from all shapes and sizes, what you start to notice is that the shapes of these tooth plates change, even within one individual. So these three photos here are one individual. Here on its right lower jaw tooth plate, you can see it's pretty rounded tooth plate outline, where here on its left side, it starts to have points. You'll get about 3 points in this jaw. And once again, it's the same individual, but this great deal of variation. So the question has to be asked, how much variation is there? And also, how are they feeding? So to answer these questions, first, look at the variation of the tooth plate shape, try to quantify it. And second, looking at the morphology of the jaw, including its shape and its mineralization. So So first, to tackle the quantifying the tooth plate shape variation, it did 2D geometric morphometrics, and to do this, you take photos of the jaws with the tooth plates intact from each side, so left, anterior, and right. And then what geometric morphometrics does is it looks at the overall shape and it is able to tell you the variation in the shape using landmarks. So landmarks are placed in the same place for all of these 47 individuals. So here are the landmarks for the lower jaw tooth plate. 1, 2, and 3 are set at the edges of the tooth plate. And then like I talked about, there's this variation in the shape, specifically the shape of this outline. So to quantify this with landmarks, you then trace this outline or trace this curve, and the program then tells you the best landmarks that represent this curve. And so you do this for each individual, and then it's similar for the upper jaw, where you have 1, 2, 3, and 4 on the edges, so same for each individual, and then this bottom edge or this curve is done the same way with these sliding landmarks. And then along with doing this for 2D geometric morphometrics, we also did this for 3D. So similar type of method where you place the landmarks on the shape, and they're placed in the same place for each individual, but here we are using CT scans. So you're placing these in a 3D environment on a 3D shape, because while these tooth plates are fairly planar structure, they are a 3D element and they do kind of curve with the jaw. So using 3D allows us to see more of the variation in the shape in accordance with this curve of the jaw and in this 3D environment. So what do these analyses look like? First, looking at the 2D geometric morphometrics for the lower jaw tooth plate, first thing you see is there is variation. Good, so what we saw just looking at the jaws is quantified here with some data. So the colored data points represent different size groupings, so blue being the smallest, green being the largest. But there appears to be no grouping with size, just variation on variation. So principal component 1 represents the overall height of the tooth plate. So here you're seeing the outline with those landmarks. So you can see this is a pretty tall tooth plate, so it's coming higher off of the jaw. Where over here on this side, you're going to see a more shorter tooth plate, so less tooth plate being seen above the jaw. And then principal component 2 is looking at, or describing this point, this main point versus up here, you have that well-rounded outline to that. So all these tooth plates down here are going to have more of these points than the ones up here that are going to be well-rounded. And now, like I said, the left and the right tooth plate vary in individuals, so why not look at both left and right lower jaw tooth plates? And we see the same thing, variation and no apparent grouping by size, and the two main principal components have to deal with the height of the tooth plate off the jaw and the presence of this point versus the rounding of these points. So now looking at the upper jaw tooth plate, we also see variation and no apparent grouping by size. So the main principal components for this is one, the overall shape of this lower edge, so this curve. And then the second principal component is the overall width of the tooth plate. So this is important to point out that this is all for the same for the left upper jaw tooth plate. And so you can see that this point here, because it's on the left, is coming down here, where this point on this side is more on this. So these variations aren't happening because it's on one side of the jaw or the other. This is all for the left upper jaw tooth plate. So now looking at this in the 3D geometric morphometric. Now keep in mind this is only 6 individuals, so once the other 40 are placed in here, I'm sure we'll see a little bit more variation, but this still, with these 6 individuals, we see variation in the shape. And for the lower jaw tooth plate, we are seeing the same type of variation. It's the height of the tooth plate and the overall rounding, so moving of these landmarks up on this upper outline. And for the upper jaw tooth plate in the 3D geometric morphometric analysis, we're seeing the same thing. We're seeing some variation, and the main principal components have to do with the width of the tooth plate, both at the top and at the bottom, this lower edge of the tooth plate. So now, like I said, we're going to look at the variation of the tooth plate shape, which we determined was very varied. And in a second, we're going to look at the jaw morphology, specifically the shape first. So to do this, we measure second moment of area, which a couple people talked about it, but in case you forgot or weren't here, I'm going to explain it a little bit. So second moment of area is the property of a cross-section. And this tells you the ability for an object to resist bending. Now, a great way to explain this is to think about a 2x4, so 2x4, and try to bend it. So your best bet to try and bend it would probably be laying it like this and bending it, versus if you set it up like this and tried to bend it, it'd be a little bit harder. And this has to do with the cross-section. So when it's like this, a little bit easier to bend, you're going to get this wide cross-section. So it's gonna be wider than it is tall, where when you have this cross-section like this, you're gonna get this tall cross-section. So it's gonna be taller than it is wider, and this plays into the second moment of area. So this taller cross-section gives it a higher second moment of area, it's better able to resist bending. So to do this with the lower jaw, I took slices from the CT scans of 10 individuals, and I took 10 slices evenly spaced from the symphysis to the jaw joint. So here's an example of what one of those cross sections look like. So here, this is the tooth plate, this is the lower jaw. You take this cross-sectional shape, I plotted it into AutoCAD, you tell it the line of force, which for the jaw is just straight down here, and with that you were able to calculate the second moment of area. So along with looking at the shape of the jaw, also looked at the possible mineralization on the jaw. Now, we did this using alizarin staining. So alizarin stains calcium. So you can see in this photo of a zebrafish, all of the bones in this fish are stained red, or if you remember Andy's amazing photos, you saw all the red from the bones of these fish. And that's what alizarin does. But Hydrolotus cholei and the convictes have cartilage, they don't have bones. But however, elasmobranchs have this neat adaptation called tesserae. And tesserae are these small mineralized tiles that surround the cartilage. And here you can see them in a stingray, or if you look really closely, a great blown up image of their cartilage, you see these tiles, tiling of 5 to 6-sided blocks that surround the cartilage. And here is a schematic of a cross-section of elasmobranch cartilage, where you have this inner core of uncalcified cartilage, and then these small, tiny little calcified blocks called tesserae that surround it. Now it's unclear if holocephalans have tesserae or some type of mineralization. So the idea is that if we place Hydrolotus cholei, its jaw, and its attached cranium, if we place this cartilage into a alizarin stain, view it under an epifluorescence microscope, we'll see if it has tesserae or some type of mineralization. So first, looking at the results of the jaw shape, the cross-sectional shape, you can see here at the symphysis, you get a little bit wider cross-section, fairly short compared to once you move back, further back on the jaw, and you start to get these taller cross-sections, and then it goes back down to a more wider than it is tall cross-section. And this translates really well to the second moment of area. So here I'm showing you the average second moment of area for the 10 individuals versus the slice location on the jaw. And you can see when we started to have those taller cross-sections, you get a much higher second moment of area compared to these cross-sectional shapes at the anterior portion of the jaw. And so what this means is that here, where you have these higher second moment of area, the jaw is better at resisting bending than it is here at the front. So this plays into the idea of how do they feed, so maybe how they're handling their prey has to do with this area where they have this better ability to resist bending. So now looking at the jaw cartilage, possible mineralization, first the lower jaw, you start looking in under the microscope, you start to see these, almost like these lining up, this pattern of mineralization. You get a better look at it on the upper jaw, and you start to see these blocks, and they look like 4-sided blocks, nicely lined up, and create this type of, has to be some type of mineralization. It varies, and it varies greatly, not only between individuals, but individuals of the same size. And now this is really interesting. Also, lower jaw resist bending better in this posterior half of the lower jaw. And like I said, yeah. Like the full animal, I would love to. Now that I know how to kind of clear the game, I'm going to do it. Yeah. So I have some that are not dissected yet, and I'm gladly.
You might be fun to get some of the other species and do the stadium morphometrics and then see if human function analysis would accidentally classify them
Yeah.
as being the same or different from your
Right.
information that you have. So that might be a fun thing to do.
Yeah, that would be a great next step to kind of see what's happening there with these shapes. Awesome. Well, thank you.
And at the dorsal side, it connects to the skull of the fish, and on the ventral side, it meets with the other half, so there's like a left and a right side to it. And the main function of it is to support the pectoral fin, which can be used for flapping, for gliding, and all sorts of pectoral fin motions. But I'm interested in understanding what happens when you bring in a pectoral spine into the situation. In this case, the first fin ray has developed into this really robust spine with these projections coming off of it. And in a case of having this really robust spine, the girdle must be different. It must be designed differently in order to support this spine and all of its abductions and erections and defensive behaviors. And so in the case of Doradus catfish, what happens is you go from the ventral view of a fish, you go from having these slender pectoral girdle bones to having a really robust ventral surface. And along the midline, you can see the suture that connects the left and the right halves, interdigitating them in a really strong way. To give you more of a sense of what these fish are, they're South American catfish that live in freshwater systems. They range in size from Phytopixis lyra, which is 1.5 inches long, to Oxydorus niger, which grows up to 4 feet long. So really big size range. And they all have these pectoral spines, which are used for defense, we presume, but also have this really cool function of being able to be ground against the other bone, the pectoral girdle bone, creating these noises that are thought to be used to communicate with conspecifics and warn against the approaches of predators and things, but I won't be talking about that today. And here's a sampling of 14 species in the Doradid catfish group. The suture that joins the left and right halves has this sinuous morphology, if you look at it from the surface of it. And what that reminded me of is a lot of other sinuous sutures that are interdigitating. For example, this turtle suture that's joining the two ribs in the carapace of the shell. And if you were to look at that suture in cross-section, it continues to have this sinuous morphology, and it actually has like a really dense set of projections that interlock in all three dimensions. But if you look at a cross-section of one of these sutures from the catfish, it looks completely different. This middle image is a coronal section, and you can kind of see a dark spot where there seems to be separation. And that's actually where like one arm is kind of sticking out in front of the other, and if you were to kind of slide through, moving, let's say, anterior through that suture, you see these kind of arms popping in front of each other, one after the other, matching those projections that you see from the surface. And then if you were to slice it along the length of the suture, you see this striking pattern, again, because you're seeing the projection of each of these arms crossing in front of each other, which is completely different from this really dense interdigitation in these other interdigitating sutures. And to me, that reminds me more of this kind of cone joint that you think of in woodworking, where you have this back and forth suture line from the surface, and then kind of just a plate-like view from the side. I dissected out a pectoral girdle of one of these catfish, and especially in this translucent view on the right, you can see kind of through the bone and see that the suture is actually really just a 2D wave that isn't curving in 3D. And it appears like perhaps that suture is allowing some flexion motion because these arms could potentially slide past each other and maybe project out if they were compressed together. And so it's interesting seeing what kinds of motions might be allowed at a suture like this. There is ligamentous tissue connecting each half, so it's not allowing a ton of motion, but it seems to be allowing for some sort of flexion in a really constrained motion. So I ran an FEA analysis, a finite element analysis. I took a CT scan scan of one of these Dorado catfish, and then loaded. I told all of the elements to have bone material properties because this is all bone, and I did not treat the suture any differently. And then I loaded the spines, compressed them at the midway along the spines where the white arrows are. And part of the findings that I found were that if you look at the posterior edge of the end of the suture where you see the blue and the orange blobs, that indicates that on the dorsal side of the suture there's compressive forces, and on the ventral side of the suture, on that same area, there's tensile forces, which would be the same as if you were to bend the girdle in that spot. You see tension on one side and compression on the other. And that's the same kind of stress regime that you would expect to cause that kind of flexion of the interdigitating arms at that suture, which seems to support that maybe that will be possible when you compress the spines. And compressing the spines might be a loading regime that they experience when a predator is trying to eat them and collapse their spines along their body. They're able to interlock them and hold them out. Small samples I had in lab, so I took a dead specimen and put it in the MTF and simply compressed it until it broke. And so as a result, I did see some breakage near the articulation with one of the barbs, but I did actually see the articulations, the interdigitating arms, poke out and kind of display themselves, poking away from the body. And I hope to continue to crush a couple more and photograph that so that I can document what that looks like and whether those arms are starting to give way and poke out before the girdle breaks in other ways. We also wanted to look more broadly among the Dorado catfish, and so here are 14 species that I looked at, and I measured the morphology of the girdle and the pectoral spines. I looked at the width of the pectoral girdle, the length of it along the suture line, the cross-sectional area along that suture line, as well as the length of the barb, the diameter, and the cross-sectional area. And then to quantify what the suture was doing, I traced the path of the suture and measured that length, and then divided that by the linear distance that suture traveled to get an index of the complexity of the path. And when I plot this on a morphospace with the phylogeny, it's a bit hard to see, but you can see that there are some species that are really spread out and are very different from the others. And then there are some that are clustering together, even though they're not maybe this closely related to their neighbors. So there's some convergence that appears to be happening among part of this. And if you map the traits onto the phylogeny, then you can also see that there are that the more closely related species have similar values to their neighbors. We ran a Pagel's lambda, or we calculated the Pagel's lambda value, and that indicated that there was a really strong phylogenetic signal to the morphological data. We also want to know whether the pectoral girdle morphology was integrated and correlated to the pectoral spine morphology. That's really what we were interested in. And when we did a partial least squares regression with accounting for the phylogeny, phylogenetic relationship, we see this really strong correlation. And if you look at that PLS correlation value plotted on a histogram, where values on the right are very integrated and those on the left are decoupled, you see that it's really strongly on the integrated side. So again, these two bones are integrated in terms of the measurements that I took. So in conclusion, when we look at this suture in this pectoral girdle, we see this really uncommon suture morphology that doesn't match the kinds of interdigitated sutures that are often talked about in the literature. And it seems to be allowing for a constrained motion that may give in the system in a way that prevents breakage at more delicate parts elsewhere in the girdle. allowing for some flexion here may protect more delicate places in the articulation from breaking. By preliminary data from the FEA analysis and the MTS impressions. And then when we looked at the actual morphological measurements, we did see that they are integrated between these. Looking further into what kinds of correlations are there and how that relates if you step back from just erotids to looking at many of the other sister groups, which also have these pectoral barbs and spines that are really robust, whether that correlation carries through as well. So with that, I would like to thank everyone who helped me, especially Matt Coleman, who helped immensely, Colin Greer for helping me with the FBA, Adam for so many informative discussions, Alice, Beth, the whole teaching staff, and all of my wonderful classmates. It's been an amazing experience. That's part of the long-term planning. I haven't had a chance to look at that, but yeah, we've talked about this, and that would be a really interesting direction to go into. Yes. That is, yeah, really interesting. There are lots of thoughts about how these pectoral spines are being used, but much more work should be done on what the actual behaviors are and how they're being loaded. We kind of put that compressive motion as a probable direction of loading, but there are thoughts that they could be interlocking their barbs with other conspecifics for fighting, or they could maybe lock them out to wedge themselves into crevices and prevent themselves from being eaten by predators, or others, a whole assortment of behaviors that these spines could be used for, which would have different loading on them and might influence the future and the girdle design differently, but definitely something that would be worth going into more, and I'm excited to look into. Yes.
Any other persons that have just not even necessarily use that technical realm, but are maybe unusually robust for kind of a bone and everything like that?
This is something that I would love to think about more, and we can talk about this later, but off the top of my head, no.
I can't either, but I'm sure there must be some, right?
I'm sure there's something. Awesome, thank you guys.
And I am a PhD student at the University of Louisiana at Lafayette. And today I would like to talk a little bit about armored scales in sygnathids, which are a group that includes seahorses and pipefish. A lot of people are familiar with seahorses and probably in a fish class. Most of you guys know pipefish too. But out in the general public, my mom was super confused by what a pipefish was. So I kind of had to explain the whole concept to her. An uncurled seahorse, and she thought it was the coolest thing ever. So, first we're going to start out with small fish. Now, small fish have a lot of things that they have to deal with in order to survive. They, first of all, can't swim very well because they're tiny, and so any sort of movement in the water is probably going to be a big challenge for them. Part of that has to do with just their tiny little fins, since they are small, they have small fins. But it also has to do with something called Reynolds number. And Reynolds number is kind of the experienced viscosity of water. So for us, swimming through water is pretty easy. We're big, we can just kind of swim and glide. For a small fish like this, swimming through regular water is kind of like us swimming through honey. It's challenging, it's stressful, and it takes a lot of energy. And so one of the things that I'm interested in is how do these small fish grow? How do they get big, and what does that all entail? Now, a lot of fish want to be big, And we look at those through ontogenetic studies. So we start with the smallest fish of this that we can find and go all the way up to the biggest one that we can find. I was able to do that through this study, luckily because we found a couple of male pipefish in our nets that were pregnant. Yes, the males were pregnant. So the males in this family are actually the ones that do the brooding. They have the fertilized eggs that are implanted either into a brood sac or into their abdomen, and then eventually they are birthed as live young. And a lot of fish, like I said, want to be big. Some of them want to be really big. But how do you get big when you start out this small? This is actually a fish. It is not just a piece of thread or something like that. I held this little guy who was born about 2 days before this picture was taken. And obviously really tiny. But it also is kind of like a thread because it doesn't have very much structure at all. And so what I wanted to figure out was, how do we get from over here, that fish that I was holding, all the way up to this fish right here, which is about 22, give or take, centimeters long. So sygnathids here are pretty interesting because they have a lot of sexual dimorphism. We have the males over here on the right that have a brood pouch within their tail, and the females have a larger abdomen than the males do. This honestly confused the heck out of me when I first saw these guys, and I was like, why are some of them really large in the tail and some of them are large in the abdomen? Turns out it's just the sex, but it's also kind of confusing. What I want to do, they actually have more protection than the females. Turns out, this is looking at kind of the tail area of a male. They don't have very much protection at all. These, right in here, those are eggs. Yeah, this guy was pregnant, which is kind of cool. And they really just have a skin flap that's kind of netted up above that brood pouch. And instead they have a structure that goes around the side. Here are some more pictures of some males and females. Up here we have female, and here's a male. This guy actually does not have any eggs at all, and so it's kind of a concave structure near his tail where a female would eventually put the eggs in order to be fertilized. So in order to do some actual science instead of just taking some cool pictures, I wanted to figure out what changes in terms of the scales with size and with sex. And in order to do that, I looked at the size of the scales, the overall surface area that is covered by these scales, the shape of the scales, and then I also did some really cool studies that included some video with GoPros in order to analyze how the fish are actually swimming across the sizes. So, obviously we all want to be big we all want to be big when we grow up. This is a CT scan of one of those juveniles, baby ones, less than the size of your finger. I don't know if you can see scales on that, but I can't. This, in contrast, is an adult mature female who actually has some structure to those scales. You can actually see how that might be useful for protection. In contrast, these guys kind of look even more like threads or worms now that we're CT scanning them. So in order to analyze this quantitatively, I looked at scale size over time with growth. And so over here, just to orient you on the x-axis, we have total length, and on the y-axis, we have what I'm calling segment length. So I took a specific part of the body through these CT scans so that I could make sure that I was kind of quantifying the same exact area in all of these individuals. So it's the area right underneath the dorsal fin, and I included the 360 degrees around the body. And when I plotted these two variables against each other, as one would expect, we saw an increase in the length of that area as the fish increased with size, which would make sense and was kind of a good thing to confirm, since a fish this big shouldn't have the same dorsal fin like this fish this big, but just wanted to check. So I went from there into determining the surface area coverage of the scales across this same exact size range. And we saw a positive correlation between these two variables. So as the fish is increasing in size, we are seeing a positive increase in the net surface area of those scales if there's isometric growth of the scale surface area throughout the growth of the actual individual. If we had pure isometric growth, we would expect this end value, the slope, to be about 1. Instead, we have a lower slope than 1, which means that these the surface area of the scales is not actually growing directly proportional to the size of the individual. Probably part of that has to do with we are making a really long tube, and so there's probably going to be some differences in the proportionality of surface area to the length when you're dealing with a tube instead of a more typical shaped fish. Just to confirm this as well, I also plotted the surface area against the diameter of this fish to kind of figure out if we are seeing a similar correlation. So I took the distance from this end up to here, so ventral to dorsal part of the fish, and also plotted that against our surface area, and we saw a similar increase in that correlation as well, with an even smaller slope. So we're seeing that it's even more pronounced that we're not seeing a proportional amount of growth in surface area to total length. I also did some geometric morphometrics. It was very preliminary, and so I apologize that I don't have percent variation or anything like that on these graphs, but from what I got here, it was kind of confusing. We had female down here, 2 males up here, female and a male, so sex wasn't the defining point of variation in this particular graph. And so this is something that I really want to look into further and see if I can get more individuals across a larger size series, so I can kind of confirm or deny what's going on with the shape aspect of it. But what I could tell from these PC axes is, this might be a little bit easier for you to tell, but this was the one side of the PC axis, all the way on the right, and this is the other. This is a male with the brood pouch right here, and this is a female. And so, like I said, I'm not sure about those non-brooding males that were over there on the left, and the female that was over there on the left, but I'm gonna figure it out eventually. We will get there. One of the cool things that I was also able to look at, like I said, was swimming. So swimming most likely changes throughout time. Up here we have a video of an individual that's about 45 millimeters long, so yay big, pretty tiny, compared to this was the 228 millimeter individual right here. I did video the smallest guys, that finger-sized fish that was swimming. If you think this is hard to see swimming, try one that's like that big and it's doing this wiggle thing. Cassandra's program was amazing, but it was not, it had no idea what was going on with that. So I was able to quantify this. And what I saw was that swimming speed increases with total length. So the swimming speed was calculated as a proportion of body length per second. And so we are seeing an increase in the ability of these adult and mature fish to swim faster than the small ones. And as I talked about before, this is likely due to Reynolds number. So we see that the large fish have a much higher Reynolds number and they're able to swim better and faster than small individuals that have a much lower Reynolds number. One of the things that I think this is, due to is just the rigidity of these individuals. So when we're looking at an individual that is this length, as I was talking about that surface area of the fish scales, we're seeing a lot higher surface area in those larger individuals, which is likely reducing the amount of flexibility in the body. Instead, we're seeing a lot of flexibility in these small individuals, likely to try to generate any type of velocity that they possibly can when they're trying to move through this particular substrate. When I look at all of the variables that I attempted to measure in all of the individuals, we have a nice little area here of significance, which is great. But we also have a lot of NAs and a lot of just kind of blank spaces. This is because, unfortunately, I wasn't able to measure every single variable in every single fish. And one of the things that I want to do is increase that sample size in order to try to fill up those gaps. In conclusion, it is not easy to be small. In the large fish, we have a much higher amount of armored scales, which is likely increasing the rigidity of that body. It's really decreasing flexibility, but it's allowing those fish to really move through the substrate in the water a lot more efficiently. In the smaller fishes, they are small, and so it's probably hard to come out of the body and come out in birth and be a fully formed miniature adult. I was hoping that that's what they're going to be, because that would be really cool. But Instead, we see a decrease in the total surface area of these individuals, which is increasing their relative flexibility. And it's likely allowing them to swim as much as they possibly can in that super viscous water that they have to survive in. And just to show you a picture of the CT scan of the baby guys, that does not look like a fish at all. So, in future directions, like I said, I'd really like to improve this sample size. I wanted to make sure that we have more of that overlap between the morphological studies and the swimming studies, so I can get a little better understanding of the relationships between those two different areas. I also would really like to quantify the morphology of this male brood pouch. And so it has been looked at in a few different species of seahorses, but it really has yet to be quantified in pipefish. Obviously, add some more specimens and a little better geometric morphometrics, add some more landmarks and be a little more specific with that analysis. And I would also like to try to reanalyze the baby tiny swimming videos that I had, but working through the contrast and everything like that, it's a little challenging. But if I could get that increased size series, it would be really, really cool. With that, I'd like to thank everyone in this room, pretty much. Instructors, especially TAs, all of the fish class. Morgan and Allie were both great. And of course the rowboat, because who doesn't want to thank a rowboat that sunk on you? And with that, I will take any questions. I forgot, I have a model of pipefish armor. Just be careful with it. I don't know if I have time.
Oh, wow.
Just to get into the realm of speculation, you know, a lot of marine fishes have pelagic eggs, and they go out into the open ocean. They may take a day or so to hatch, and then you have a larva that has to undergo transformation. Are your pipefishes better off the way they are, or I mean, what happens to those little guys? Are they going to be picked off as readily as a pelagic larva?
I think they are. And so I think that's one of the reasons why the adults just give birth to so many of them. So we had 2 males give birth within the span of 8 hours in the lab setting, and there are probably 200 juvenile offspring between those two. In the span of 8 hours, 2 individuals gave birth to 200 individuals. And by the time about 9 days had gone past, over 100 of those individuals were dead. And this didn't even include any predation in our lab. And so there's just kind of a lot of, I think it's case-selected sexual.
So let me tell you a little bit of me talking to you about egg cases. So I have a model here, and I'll pass it around. You can take a look at it. So generally, it's not purses like pocketbooks, actually, play on words. So egg cases, chondrichthy fishes, which some people have introduced to you already, our sharks, our chimeras, and our skates actually lay egg cases when they're going to have live birth. Now, keep in mind that with our sharks, it's not all of sharks. Some sharks are going to have live birth, and they will have eggs that hatch inside. But today, I'm speaking specifically on those that are going to lay eggs. So inside of these, they actually range in shapes and sizes. Like the one, for instance, that's being passed around, that's actually 50% less of what the size is. So to give you an idea, our chimeras, okay, so our spookfish, our ratfish, our elephantfish, they actually have 3 different morphotypes, as you see right here. For our Calorhynchus, our rhino chimeras, and our chimeras. So you see here, the main distinct difference is realistically the fringe along the side. So this one right here, the Calorhynchi, is the one that is being passed around. Okay. So another type, we have the morphotypes are the ratcherites, our skates. Okay, so you notice here that they come in different shapes and also different sizes. Here, when I reference the horns, this is what we're talking about right here when we discuss the horns. You notice again that the horns are going to be in different lengths. So here, these are for our sharks. And our sharks are separated into 3 main morphotypes. You notice here, even though these, actually, we have some that have horizontal or actually vertical lines along the exterior, Some are totally smooth, which brings minds like, why are they so different? Okay? And circled here as well, this is what, when I talk about tendrils, that's what I'm discussing. These are tendrils, actually. And they're going to act as ideas like when you have a balloon and a string, realistically, to tie it down. Okay? Some are going to lack the tendrils altogether, and then some are going to actually be spiral. So these right here are bullheads, like if you're familiar with Port Jacksons, okay, and zebra bullhead sharks, but you notice here that they have distinctly different spirals. So now, taking into consideration these A cases, general model, and when we're thinking about the fluid dynamics, okay, water goes in, water comes out, easy, seems fair enough, okay? But then you have the idea, okay, if you are going to add a baby skate, okay, and then a yolk sac, what happens here? Is it going to cause vortexes? Is it going to go straight through? Is it going to be lost? What's going to actually happen? Now, if you're not familiar also, this yolk sac and this embryo are going to take sometimes months, even years, to develop inside. And these egg cases are going to lay on the bottom or be attached to a substrate in the ocean. They're not cared for, they're not nurtured, just like our fish, we're all familiar that the eggs are going to be dropped and then they're going to be left for their own to develop. So what happens? This is our big question. What happens through this development period? A lot of studies have looked at the development in itself of the embryo and size relationships, things like that, but nobody realistically has been looking on the flow, okay? Even though there are publications about the ventilation, the oxygen, because understand again that they're surviving in this area, but they're going, how much oxygen do they get? How are they going to release anything? How are they going to gain more? These are the questions that I was looking at. So let's go backwards, because instead of using all of the high-tech stuff, which was really awesome in Cool Beans, but you take a full class, the largest fish class that we had here, and things break a little bit, okay? And we run out of stuff. So we make things to take effect, whether it's hanging, it's sitting, it's laying, it's resting in a specific angle or position as opposed to or in relation to the substrate. So I played around with the different angles, figured out ways of having it suspended, having it sit, having it at, mainly I looked at 45 and 315 degrees. Another thing is it has been, there we go, we see movement and we see a little bit of jiggle right there, okay? Because it is published that skates, because they're going to rest, they are not going to be in the movement, swaying in the air, they're going to be sitting at the bottom, and in order to help, let's do that again so you can see it, in order to help with that movement, they actually undulate their tails. So with the help of Alice, thank you very much, and Amazon's quick prime delivery, we got this little hydrobot in there actually causing a little movement. And in addition, when Jules is struggling trying to make Jell-O and being like, okay, stir, 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 I'm a very impatient person, so I'm not going to stand there and stir. I went searching for a stirrer. So I found one, and believe it or not, putting it underneath the flume, it actually was able to pick it up and it could jiggle it. So we have high speed and we have low speed. I was able to look at those two dynamics. So, mind you, okay, this is me, this is where I was. Generally, when everybody's like, where are you going to do your data? You'd see me like walking around with all of these little pipettes and everything, and I went to the dungeon, which, by the way, this awesome machine is like hidden in the back. If you go through the chemical hazard waste closet, then there's a room back there. So I had to like hold my breath and then go in. Yeah, fun times at night with a contact high. So, giving you an idea, this is how I looked at it. Because I don't know about you, but if you look at that, I'm like, depending on what the light is, the blue wall kind of looks the same. So obviously I'm doing it more high-tech, bring into some equipment. So what I was doing, I'm going to go back for a second, you see that I had a standard concentration of a blue dye. For my, I had a big jug and I created this dye, okay? So I had that as my standard and my control. And obviously, as it was being released, it was losing it, therefore it was becoming less concentrated, it was diluting. And that's how I was going to understand the relationship of my flow. So here comes in play the, is it really dark blue, is it really light blue? Looking at the wavelength and looking at the absorption. So this is what I got, okay? So understand internal concentration. So as we're decreasing, we're talking about the flow is actually faster because it's less diluted. It's less concentrated and it's more diluted because more of the fresh water has penetrated through and circulated through the egg case model. Okay? Internal mass. Remember I was talking about the idea that I played around with placing things inside to take up that, what would have been free space. Okay? So don't mind my little military numbers or anything, but understand that Hotel at Nadia, those were my gallon jug and my half-gallon jug. Okay, so I played with the larger ones, and I saw, okay, there was a nice little curve in the concept that as I'm going to increase the mass, it actually speeds up the flow, which you think, understand, because again, you have this space inside, it slows down. You decrease that space, it's going to speed up. However, then when I incorporated Charlie and Golf, which my half liter, and then my 1 liter, we see that it actually is going to increase in concentration, meaning that the flow decreases, the rate of flow decreases through the model as I incorporated more mass inside, which made me think, okay, is it better to be bigger? Is it better to be smaller? So it brought me back to my morphological constraints. So for these, I was specifically looking at those that related, my models related to those of the chimeras, with one tube in the front anterior and one in posterior. Those are the fissures, if you will, okay? So when we made these models, I made them look a little closer. Okay, not bad, in my opinion. Okay, I tried to mimic, this is an actual, this is a schematic, and this was my model that I tried here, my foxtrots, okay? I got from a larger, continued to get smaller and smaller, tried to get as close to the volume that would actually go through this egg case. And we see a little bit as wonky. Okay, so this makes me think, okay, it's not necessarily larger, it's not necessarily smaller. What is actually going to impact that flow? Which brought me back to the models. And I had CT scans, and I looked out a little bit further, which brings me to some investigation that I want to do further. Right here, there are these teeth, okay? Which makes me think, okay, is water actually escaping these? Do they open up during the development? Are they open the entire time? Because again, it's not documented that the chimeras are going to pulse, just like the skates, but you look at it and say, okay, it's here. No, this is a blown up from right here, but they're also right there. It's not the entire egg case that's zippered up. It's just the anterior and posterior ends that have those tube-like structures. So what do? That's a future investigation. So another thing that I discussed is the concept that I looked at angles, because it has been documented that having them rest at certain angles in proportion to the substrate will actually affect that flow. So here, keep in mind, you don't have to worry about which model this is, okay, or which development, because all across the board, no matter if it was 50% filled, 75% filled, 0, or whichever model that I had represented here, regardless of it, there were always a decrease when I brought into the idea of creating an angle. So for example, you see here, when it was resting, this was a high concentration, which meant a low flow rate. Introduce an angle, bam, drop down. Drop down my concentration, meaning my flow got faster, okay? So these are some of the examples. So longer fissures on both anterior and posterior. Some, just like the sharks, having done away with the horns because they have the little fissures, so I have little opening slits on the sides. This brings into the idea of further investigation of really looking into these models and actually recreating some that are closely resembling the egg cases themselves. Which brought me into a real life issue, because as we arrived here, Adam said, hey, we have an egg case. You want to look at egg cases? This is awesome. We have some. And I was like, okay, when are they going to hatch? When are they going to hatch? And no, they weren't going to hatch. The idea wasn't to take them. So I was like, all right, I'm gonna try to do all the morphology and looking at it and taking all the measurements, and I tried so many ways of recreating it, days and nights spent trying to recreate it. And at the end of the day, one day Adam comes to me and is like, okay, well, if I kind of like the models that you're going with, all right, they seem pretty good. So I was given a challenge if I could recreate or manufacture a new one. So here comes the math, because now I have life in my hands, and I was like, okay, I can feel the move. I've never been maternal, but I can feel the move, and oh, I get to recreate a womb, and this is wicked awesome blue beans. So I was super excited. Carly was there, thankfully. Yay, photo tag credits. Okay, so I've been given this task, and thankfully Alice comes to me, and we're looking at Adam's paper and looking at metabolic rate. So taking into consideration the flow exchange of the models that I made, and the weight in which, not one, 7 little babies inside, 7 embryos, plus their yolk sac, taking into consideration the lack of water and volume that they would be taking up, okay? So they're taking up that space, how much water is left over, how much oxygen is actually within that available for them, how much they are going to be taking, and my exchange rate, will they survive? And I did it. So if you go into the lab, you will see these little babies growing, and Carly is going to be taking videos and updates so you can see these little guys. And it makes you think, depending on the flow, are they going to speed up their undulation? Are they going to slow down their undulation? Who knows? We will stay tuned. So future investigations, really looking at the external base flow, because I wasn't able to recreate the models, but I want to be able to recreate actual models based on the egg cases themselves to really look at the external fluid dynamics. Also investigate the internal, like using the actual molds, silicone molds or clear molds, that way I can really see what's going on inside of it. And then explore the flow, just like what I did, but changing the different speeds. And with that, I just want to thank Dr. Fleming, who has been like an inspiration, everybody, Fish Biomechanics, okay, Sabrina, who as working, oh my goodness, support, because all of a sudden I was like, oh, it's been 4 days. Oh wow, I didn't even realize time has gone by, calculations and everything. For all of my samples that I've been given, everybody here, thank you very much.
Unfortunately, we're out of time, so we'll have to catch you again later.
All right, thank you.
New Jersey accent.
All right. So today we're gonna change it up a little bit. I'm an ecologist. I'm not a biomechanist. So I'm gonna tell you about the sculpin sand wiggle, which is an amazing thing that sculpins do, and what it tells us about fish ecology. So first, I'm gonna introduce you to our fish. This is one of them. This is very cute. I'm gonna tell you what questions I asked, how I designed my experiment, and what happened, and then most importantly, why this is important, why should we care about the sculpins wiggling, and where we're gonna go from here. So, without further ado, let's meet the fish. This is Lepicotus armatus, the Pacific staghorn sculpin. They live right here, anywhere between Mexico and Alaska. They eat anything that fits in their mouth. Sometimes they eat things that don't fit in their mouth, but they prefer crabs, shrimp, and other fish. You can tell them apart from other sculpins by these really sharp, vicious opercular spines, and by the black spot on their dorsal fin, as well as this really nice rounded head and mouth that you can fit large amounts of food into. So like I said, they live in intertidal sandy flats between Alaska and Mexico, and that's really important because they have a really interesting behavior that allows them to live in that sort of bland environment without any shelter. So they can essentially bury themselves entirely in the sand, We have two sculpins right here, in case you can't see them. There they are. This is one eye and the other eye, and then right here, one eye and the other eye. So they're very, very good at that. And the way they do that is kind of amazing. So I call it the sculpin sand wiggle. It's done by laterally moving their body back and forth while they're bashing their head violently. It's super cute, and the big ones can entirely bury themselves in the sand. Like we're gonna see right here. Somewhere. It's worth the wait, I promise.
Did you make it in Google Slides?
I did.
Then it won't. Sorry.
Okay, well, you're not gonna see. But basically, if I was a sculpin, I would wiggle my body back and forth, back my head. Come back to me and I'll show you the video later. That's better than that, I promise. All right, so I am neither a biomechanist nor a fish person. So I wanted to start with a really easy question. And I decided that because I'm a scientist, I'm going to go in a little more depth than that. So I wanted to know how do leptoconis make use of their available habitat. So around here, they have rocks and pebbles, they have tide pools and sand. So how are they using what's available to survive? And taking that information, how does this differ with scale? Because we have a bunch of fish ranging from 4 centimeters to 30 centimeters, and so it was a really good sample to do scaling projects. So I needed to design an experiment that would allow me to look at mass and size, movement patterns, and habitat preference, while still taking into account the fact that working with live fish is really hard, and sometimes they don't do what you want them to do. So I spent a lot of time just looking at tanks, being like, come on, please, and they didn't care. So I set up a tank with 4 substrate options, going from large rocks to pebbles to sand. And I put my fish in that tank, and I sat in a bucket, and I watched them for 2 weeks. So habitat preference trials involve putting a fish in the substrate and waiting for 30 minutes while it explored its options, and then recording the position and the area that it was in every minute for the next 30 minutes. I also did movement analysis while I filmed a time lapse of fish over a period of several hours and analyzed the footage using XMA Lab and ImageJ. So you can get a lot of stuff from these little sort of little graphs or figures. So this fish right here moved all over the place like crazy, but it seems to like this little corner right here. Why? I have no idea. They do a lot of things that I don't understand. Versus this fish spent very little time moving, and it essentially buried itself in the sand and then barely moved again. So what did we see? Remember, these are our questions. How are they using the habitat, and how is that behavior changing with size? So we saw no correlation between size and habitat preference. So I'm going to walk you through this graph. I looked at time with sand against fish length, and got something like this. So let me tell you what this means. This doesn't mean anything at all. It's a nice figure that basically tells us my sample was not big enough to tell what they were going to do and what preference they had. But not all is lost, because I found that fish in general prefer sandy habitat. So when I took a step back and a deep breath, and I took out size and just looked at where fish were spending time in general, this right here is percentage of time, and this is which substrate. And you can see they really like sand, which makes sense because they live in sand. Here, you have one that's enjoying sand. So in terms of movement analysis, I got a pretty strong negative correlation between fish size and movement. So I looked at body length, right here, and fish length, and you can see bigger fish move less, and that actually makes a lot of sense. However, we had no correlation between mass and movement, which is really interesting. So when I looked at the exact same body length versus fish mass, I didn't get anything. And I have a theory that I haven't quite investigated yet, that there's a really complex dominant structure in a tank filled with fish. And so some of the fish are getting all the food, and it's not necessarily the individuals that you would think. It's mostly just the ones that are willing to fight off the other fish, and they do that in a really aggressive way, and you'll have tiny ones attack big ones just right in the face. So I don't know what creates that dominant structure, but they have very defined personalities, if you'll allow me that word for fish. So I think maybe it's just the tougher ones. So why is this so important? First of all, it's super cute. We learned that fish are individuals and that some are more nervous than others. So we had a lot of fish that were put in the tank, and they just examined each substrate very carefully, chose one that they liked, and just hunkered down and chilled. And then we had some fish that just shot all over the tank the whole time and had no idea where they were and were very upset about it. And then you have fish 17 that buried itself halfway between two substrates and didn't move for 4 hours. So that was great. But we know that fish prefer sandy habitat in general, and this has implications for conservation. So especially lately, a lot of our wild natural spaces are under attack, and there's a lot of changes that are happening to the habitat. So if we know that fish prefer a certain area throughout their range, and that area is being destroyed by development, then we could lose these fish, and that would be awful because they are amazing. So in terms of movement analysis, small fish move more, and they move more frequently. And I think that this is because they're harder to see on every substrate. They're smaller, and they don't bury themselves very well. They don't seem to be able to get their head all the way under the sand. They also have a higher metabolism just because of their small size, and they need to hunt regularly for food. And I saw them hunting constantly in the tanks versus the large ones just bury themselves. The large ones also have lower metabolism, and they need to be under the substrate to hide from predators. So where do we go from here? I saw some really, really cool color change in sculpins that is pretty much undocumented, and nobody really knows what's going on here. So these are two fish that were the exact same color in sand, and then we put fish 16 here in rocks. And it not only mimicked the dark parts of the rocks, but it developed these white spots to mimic, presumably, these white rocks. So that's a really cool, complicated color change. And it seems to happen mostly with the big fish. So it's possible that if their habitat is changing or disappearing, they're able to adapt to a different habitat and survive even if they can't bury themselves. So I'm going to come back to Friday Harbor in 2 weeks, and I'm going to put some sculpins on some color changing things, and I'm going to see what they do, and I'll keep you posted because it's amazing. So I have so many people to thank for this. Friday Harbor Labs, Adam, Alice, Sarah, and Cassandra for emotional support. They're awesome. And MC, and Hannah, and Cassie for help with R, and Ellie for chocolate, because that chick just shows up and just puts chocolate on you and then leaves. And obviously, Leanne, Renee, Andy, and Jules is not on here, but they all brought me food, which was great. And food and late night snacks is clearly in my heart, so I'll take your questions.
I'm going to try to pull up your video.
Okay. Oh yeah, 'cause I haven't humiliated myself.
You've got questions.
We might consider plotting your mass against just distance move, not body length move.
Well, so I took 2 masses before and after I dumped a bunch of food in the tank, and some of them were the same mass and some of them were entirely different mass, and it seems to be irrelevant with height. So, and I saw some of them just like pull, one of them pulled food out of another one's mouth.
I think that there's just a little bit of a problem because you have the size in both axes, and I think that makes life a little more complicated, so we could talk about this.
Yes, I would love to, because it's weird.
You obviously think these fish are pretty smart. Do you think there's any learned behavior with regard to this? They slow down. You said the bigger ones don't move as much. Are they, slowing down because they figured out where they'd rather be?
Learned behavior is actually what I do. So I would love to look into that, but I don't know. They definitely figure out very quickly when you're changing the substrate and they move to the one that they like, and they associate you with food within 2 days. So they definitely can learn it.
Well, sorry.
Oh, that's okay. Come see me later. It's really cute. All right.
That color change is really awesome. It's really awesome.
Certainly not least.
Oh yeah, yeah. Yeah, the stuff with flatfish show that they'll mimic a checkerboard. And nobody knows how because they can't see the checkerboard.
Just yell at everyone to be quiet.
All right.
We ready?
Certainly not least.
First of all, before we get into my talk, I just want to say congratulations to everybody. All your talks were amazing. I think we did a great job of this last month and a half, actually. And as someone who got to sit and watch all of them before hers, I can say you all did a really great job. Amazing projects. And I think we all did a lot of work in the last couple weeks. So anyway, in order to finish you off, if you are having to be falling asleep, just pay attention to the beautiful pictures. If you want to pay attention to the actual data, try to focus a little. But I am also going to be doing a talk on deep sea fishes, which is primarily what I've done at the University of Kansas. And so today we're going to be talking about a group called the recurrent fishes, or the rat tails. And we're going to be looking at changes in their bone density. So just to give you a little bit of background information on the ocean and some of its abiotic factors, we have our fun pelagic environment. We have both pelagic and demersal benthic environments. But just to give you some of the different characteristics of the ocean, we have a characteristic of light and light changing with depth. And so right around by 1,000 meters, we have a loss of pretty much all light in the ocean. We have a change of temperature where you have kind of a drastic drop in temperature in the first 1,000, 2,000 meters. And then all the way down by 11,000 meters, which is what we know of as the deepest part of the ocean currently, you are down to that fishes have evolved as they kind of invade these deep sea areas. One of the things that is a problem for fish is the fact that these gas ladders that they use for buoyancy in the water column and just to kind of go up and down. And as you increase pressure and increase depth, you actually have an increase in the density of that air cavity, and so the air isn't being as helpful for your buoyancy. And so some of the things that you can do in the deep sea to kind of help with your buoyancy issues, because you may or may not be able to use that gas ladder efficiently, are to decrease your mineralization, which would increase, decrease the density of your body. And so this is just a graphic to kind of show you that there are differences and variations in different mineral concentrations in different fish. So down here we've got some chondrichthyans where we've got more water percent and less mineralization, whereas within the beaked whale you've got like almost 100% mineralization, which is kind of crazy. But this hasn't really been studied across fishes at all. We did have a talk earlier this month given by Abby, who did a great job talking about snailfishes and their bone densities, but today I'm going to be talking to you about the rat tails, because we've kind of changed only the grenadiers, not the rat tails. And so these guys are demersal fish generally. They live on continental slopes. Are there differences in these densities between bones? So are some bones more dense, or some bones less dense? So and then bone density decrease with depth, which is kind of our main overall question. And I think that we might, or at least I thought that might be something like that, where we'd have a decrease in density as we got deeper in the ocean. And then just to kind of address this talk about phylogenetics, to see whether or not there's a phylogenetic influence on the variation in these bones as well. So we use specimens from both Scripps and the Burke Museum. I had 11 recurrent specimens and 1 outgroup take specimen, and these are alcohol preserved. And we CT scanned them. It took a while, as all of you know, and have at least tried the CT scanner.
It's super fun, but it takes a long time. I reconstructed them in NRECon and then I cropped them in Data Viewer. And the process takes a lot longer than you would expect first coming into it. And I did a lot of work on my one true love, Amira. Oh, actually, before we get to Amira, because Amira's the best part, how do we calculate bone density in these fish? So we actually use something called a phantom, and the phantom is of a known density, which is associated with hydroxyapatite, which is the mineralization in bones. So you have two different densities of this within a CT scan. So one would be the 75% hydroxyapatite, and then another would be 25%. So what you do is you plot that baby in with your CT scan, and then the voxel brightness between these two will give you an approximate density within the rest of your fish. Anyway, so Amira was used to partition out all these beautiful bones. Anyone that walked into the printer room over the last 3 weeks, that's where I was all of the time. Before anyone asks, since you will be seeing a lot of these images, this is the nasal. It projects out of all of the macrurids, or most of the macrurids. There's a few that it's not so much, but it's kind of neat and kind of crazy, but it's not as crazy as a paddlefish, so don't think that. The rostrum come out a little bit. I don't know what it does. So the bones that I actually looked at and found densities for were the 11th vertebrae, the pelvic girdle, the lower jaw and its associated teeth, and the first trigeo-4. And I chose these bones because I thought there may be varying constraints on the evolution of these bones. You may get a loss of density in the pelvic girdle. It might not be used as much in Betmoyo DC fishes. You may have a more constrained density of you kind of wanted to. I also did a phylogeny just using 3 different genes. I think that's mineralization. Some up here is 50% mineralization. And then the second question is, do these bones vary across this specimen itself? And you can see that actually, yes, they do in a very regular way across all of the specimens. So in general, the pelvic girdle was then, let's say, the vertebrae and the trigeo-4, and then the lower jaw actually had a statistically significant difference between these other 3, where it was always higher than the other ones. And I'm going to walk you through so you can finally see whether or not bone density varies with depth. So on this side, we're going to have depth, and then on this side, you have hydroxyapatite. And so we have our hake, and our hake falls right around the 42% range. And again, these are averages of the 4 bones that I specifically measured. It would be good to also continue this work and look at other bones as well. To move down our depth range, we have Caesorchis, Scyphopsis, and Aconcagua. I can never say that one. But we have a drop in the density, so it's like, all right, we might have this cool, awesome trend. But I went to a studies here looking at, and my favorite is associated with a certain color range within Amira, and they're kind of they're transformed so you can see, or you can kind of compare densities between the images themselves. So we've got some really low density ones, some high density ones, but there's no major correlation with depth. This is my phylogenetic tree. I was excited because Corpinoides fell together, Caesorchis fell together, and Bizumia is right next to them. So this is a very normal phylogenetic tree for this group. I used a Langham fish out group because I had to, because of my group study, and then a beard fish as well. So looking at this tree, I did a quick ancestral character state reconstruction and trace density across it. It's a parsimony analysis I would actually like to do, like we did analysis. But you can see there's also no correlation with phylogeny. We've got a sister to a really high density one, and it ranges and varies all across the tree. So hey, why not look at length? We might as well. And so I total length and make it with, you know, there could possibly be a trend here, but we only have like 9 data points. So in order to essentially look at this more, we may want to sample more species and see if we can find an actual correlation with body length. Interesting as well. We did find variation in bone density. We also found that they varied within a specimen, but we did not find a correlate phylogenetic influence. So what might be happening? Some speculation here. A lot of the deeper living fishes, you you can see here, have extremely broad ranges. And so this broad range may in some way be inhibiting some sort of effect of bone density decreases because you're finding them in all the way up to 4,000, huge range. So that could possibly be having an effect. We also have this potential, again, from the phylogeny effect, is that the phylogeny or the specimen in the study really going all within this plate here, and then the specimen is zooming up here. So sampling more broadly across this, we might find more. It could be acting on whether or not they are not having a decrease in bone density. And then something else too to think about is the fact that they could be losing numbers of bones, which Adam has actually mentioned to me before. So looking into that to see if there's a decrease maybe in the number of vertebrae or in the number of ravens to actually decrease this density of the mineralization. All right. So with that, I would like to thank everybody. You've all been amazing and great, and I have learned so many things here, especially how to use a CT scanner and a MIRA. But I want to especially thank Mackenzie for allowing me to work on this project, and the facilities here at Friday.
More than other things, if you tried looking at jaw mineralization.
The only reason I felt confident in lumping them together is because there was such a consistent trend that the increase of the jaw mineralization for that average increased for all of them, right? But that isn't necessarily to say that there is something.
Yeah, there's a few lines that cross.
There was one or two lines that crossed.
The other thing I was wondering is, I know that, you know, with 9-point girls kind of looked at it,
Yeah.
but I mean, my eye would suggest that there's, from the line, and then seeing if those show some sort of depth, it was like for the size, you have more ossification.
Right, right. And we do have more specimens, actually smaller specimens too, that we can take a look at that. It's just obviously time constraints.
Oh, yeah, no, it's
But
just
no,
a good feature.
we definitely have some that we could scan again and then get additional data on that, because then we could compare a specimen that was bigger of the same species and a smaller one to see if there's differences in ossification just within the same species too, which would be nice.
Yeah, beautiful.
So,
Thanks.
Have you tried to correlate any of this data with collection data, like when they were collected, how long ago, where,
I have not, no, but
things
that's-
like that? You know, how long have they been in a fixative? And
Well, and that is another issue. I did take a look at otoliths, and a lot of them had either degenerated to the point where they weren't there, and you can't necessarily use the phantom to calculate hydroxyapatite for otoliths because they're made of something a little different. But yeah, you could potentially have a loss of mineralization in the bones based on how long they've been fixed. I haven't looked at that, but as a preliminary study, and I want to continue with this, and I want to get this at least published somewhere. So looking at something like that would be good, especially for the discussion as well. Anna.
Just in general, how much we know about the development, what the term bone density in fishes, like it's a plastic developmental thing, if it's like purely heritable, if it's somewhere in between, if they're, happen somewhere diversely.
Right. I don't know. I mean, that is, I have to read up on it. I completely say I don't know, but when I do.
Interesting.
Yeah.